All right, welcome to the second day of this week. Talking about rotation. We kind of left off yesterday where we looked at the relationship between rotational kinetic variables and how to go between that. Remember, it's basically based off the radius. That's going to be really beneficial for us to understand what's going on with these relationships. The radius of an object's from its axis of rotation is going to be really important. Now, the key is the axis of rotation. So I'm going to quick run through today what's going to be the moment of inertia and how is it compared to mass. Then tomorrow we'll get into torque and see how that compares also with force. But this is kind of our second unit, or dynamics unit, understanding the connections between our second unit to the rotational version of it. So first, kind of the basis understanding of what we looked at from our first second unit. In our second unit, we discussed Newton's first law, or the law of inertia. Um, we realized the relationship between mass of an object and its inertia is direct. Inertia and mass go hand to hand. If you have an object with a lot of mass, its inertia is going to be great. It wants to resist change in movement. Now I'm going to talk about rotating objects and see how mass changes that outcome along with with it in terms of rotating objects. So this is a new concept. It's called moment of inertia, and it's represented by capital I. Easy kind of thing for that, just I inertia, but now it's moment. I don't know why they didn't use that for your mass, but whatever, because we already used the lowercase m. But on your equation sheet, it's going to be labeled rotational inertia. Moment of inertia is what I've heard in every class I took. I think the only AP board really does the rotational inertia. But the simple equation I'm going to give it to you right now is going to be the sum of all your masses, your individual points of mass, times your radius of that mass squared. All right. This is going to be helpful for us to understand where this is coming from and mathematically what does it actually mean. This radius is a radius from the axis of rotation. All right. The mass of a given object is always constant, and then can the same be said for the moment of inertia? So an object's mass will always stay constant, but the moment of inertia can it change? And we're going to realize yes, because we can actually change our axis of rotation on an object. So it can change. So no, it depends on the configuration of the rigid object and where its axis of rotation is located. So if pretend I have like a circle here, or a sphere, and I have an axis of rotation through the middle, it's going to have one type of moment of inertia compared to the one where the axis of rotation is on the outside with this circle here, and it's outside there. That's going to be something to keep in mind and understand where it comes from. Now, this equation of moment of inertia, it's going to be the sum of your masses times your radius squared. I think of this as your object has an individual point of mass, and every object, if you break it down to a bunch of small pieces of masses, then you can actually start calculating your radius from or your moment of inertia from that. So we take one bit of mass and multiply by its radius squared wherever that mass is located, plus another bit of mass in wherever radius that mass is located. You add up to it until you get the sum of it. That's going to be your moment of inertia. If more of the little pieces of the rotating objects are located further away from the axis of rotation, then the moment of inertia will be greater than an object at the same mass where the more of the mass is concentrated near the axis of rotation. So this is the idea of a spinning chair. If you have your spinning chair, this is actually what changes figure skaters' speed when they do twirls and jumps through the air. If you have your arms out, your moment of inertia is going to be greater, which allows you to move slower because you're going to resist more change in movement. But once you bring those arms in, then your moment of inertia is going to be it is decreasing quickly, and that's how you're going to actually speed up, because you basically changed your moment of inertia, which means the motion before is now going to be accelerating as you're changing it. Now, this page, let's just pause the video, kind of get a good look at this and reference some of these equations. Maybe have it out next to you when you do the worksheet today. But your basic one, the easiest one to remember, all these different shapes have different moment of inertias. For AP Physics 1 kids, they'll give this to you. This hoop and cylinder shape, it's your mass times radius squared. Simple enough for there. A hollowed cylinder, you're going to take your radius of your outer minus inner. Your full one's going to be 1/2 mass times radius, but then it gets to the weird shapes where it's going to be a rectangular plate. This is going to be 1/12 mass times your a squared plus b squared for your lengths, and then it's going to be your thin rods and long, or both your rods, which is going to be the axis of rotation in the middle, and then on the edge of this rod here. So you're kind of twirling around. This one you're just twirling with your fingers like a pencil. Notice your moment of inertia is going to change just by moving that. The object hasn't changed, but you're just moving your axis of rotation. That's going to change your moment of inertia. Then a solid and hollow sphere. So main thing, pretend all these objects have the same mass and the same radius for the matching ones. Notice the equations are different. In the AP Physics C, your equation should look familiar, something that you should know. When you have all these summations, you should be able to realize that you can actually do an integral. In this one, you're probably going to do some integrals with this. Your thin rods, they'll probably be really thin rods. You won't be able to do three-dimensional. They don't go for that far. For you guys, that's more of a Calc 3 topic. They don't expect you to know Calc 3. But these three-dimensional objects, they won't really touch much later. But calculus is kind of how you actually figure out the moment of inertia. So just as mass is different as the resistance of an object accelerates due to the applied force, the moment of inertia is a measurement of an object's resistance to angular acceleration due to applied torque, which is what we're going to talk about tomorrow. The greater the moment of inertia of an object, the less it will accelerate due to the applied torque. So more moment of inertia, less acceleration. If we apply the same torque, which we'll talk about tomorrow, to a solid cylinder or rectangular plate, what's going to be the difference? This is all going to be based off of the moment of inertia here. The smaller one's not going to get as much acceleration. Which object has the greatest angular acceleration? You can go back in the slide and check it out. We won't do that. Since for the answer to this, since the rectangular plate has a smaller moment of inertia, greater acceleration. The angular acceleration can be different for the same objects if the different axis of rotation is chosen. This is what we saw with the rod. And this is the last question here. If you want to rotate from rest a long, thin rod, where should you hold the rod to make it easier to rotate? It's the one that, if you want to make it easier to rotate, you want to figure out which one has the smaller moment of inertia, which is going to be the position where you're rotating in the middle instead of the end, which makes sense because you have to move the whole rod while you're just moving half the rod over here. And you can see this is 1/12 of your mass times your length squared. This is 1/3 times your mass times your length squared there. So that's going to wrap up just understand what the moment of inertia is for you guys. A few tasks for you to do here. I want you to watch this video on YouTube that I'm going to post for you guys. This is just an old physics teacher. He's doing some of these ramps. This would be the demonstration I would have done in class. Kind of showed with you, walked it through with you guys about moment of inertia, but he does it pretty well also. And then another worksheet. This one's also due Friday. This is dealing with moment of inertia. If you take a picture of that slide, I suggest doing that with all the moments of inertia. This is kind of the relation, direct relation of it. If you double this, what happens to this? something that you really need to understand. That's probably what they're going to be quizzing you on. When you're doing this, anytime it mentions torque, don't need to answer it. I think only the last one does that. Um, don't do the last one, A, and also B, because we haven't talked about the energy yet in rotation form. But you can see where this is heading. We're going to talk about torque tomorrow. Friday is going to be basically going over all these worksheets and making sure give you my work on it so you can check, ask questions, and figure out what to do from there. But hopefully you pick something up from this, and we'll keep moving along. Um, if you have any questions, always ask and send me emails. Go to Google Hangouts or do whatever.